estimate mu, which is the average commute time. So we're going to do the same thing. And we had we solved the normal distribution, right? And then we said, oh no, we're not going to use sigma this time because we can't have sigma because I want to make sure I end up in the T box. All right, so sum of normal distribution, estimate mu, average commute time, and we said, well, 1 minus alpha is equal to 0.95, so we're still going to have 95% confidence. We'll say that n is equal to 100 like it was before. We're also going to say that when we did x bar the calculation, it came out to be, what was it, 87? Mm-hmm. So it was 87 minutes. And instead of sigma being, what was it, 10? I don't remember.
15.
15, we'll say S is equal to 15 minutes. And what's S? Sample standard deviation, meaning what? You probably have to calculate sometime in Stat 2 the sample standard deviation if I give you data. And I think I had said to my statistics 1 class, and I'll say it to my statistics 2 class. Every test that you have, you're going to, at a minimum, do 2 things. I'm going to give you data, and you're going to have to calculate the sample mean. Nobody ever gets that wrong. But also, I'm going to say calculate the sample standard deviation. So you have to understand how to calculate a sample standard deviation. That's in chapter 3. Okay, and so we had the review of that last week, so make sure you're familiar with the sample standard deviation. Okay? How do you calculate that? So, all right, so we're estimating mu, average commute time. All the data is the same except we have S instead of sigma. And so if you're constructing a confidence interval for mu in this case, what kind of a distribution do we have here? It says, is the population normal?
Yes.
And the answer is yes. Is the population standard deviation known?
No.
And the answer is no, and you have a t-distribution. Everybody see? Correct t-distribution. Okay, so what is a t-distribution? Well, the t-distribution is a normal distribution. And so it's explained on page 307, 308, t-distribution. Basically, it looks something like this. There will be t's down here, and this will be the distribution when n is equal to 100. Graphically, it will look something like that. What's that? That's a normal distribution, it's symmetrical, bell-shaped, etc. Okay? Let's say that n is equal to 50. Well, it looks something like this. Well, that's a symmetrical distribution too, except that it has more dispersion. It's a little fatter than when n is equal to 100. So when n is equal to 100, it looks more like the z distribution. When n is at 50, it looks less like the z distribution. And so the t-distribution is a function of the sample size. You have to know the sample size in order to derive the t score. You know how we derived the z-score? We said it was 1.96 with 95% confidence, 2.57 with 99% confidence. That came from the t-table. So what you do is you look at it came from the z-table. You look at the z, find the area, you pluck off the z, you put it into the formula. Over here, you have to use the t-distribution. And so how do you read the t-table? So there's another table in this textbook on the back flap of the textbook, and it's also one of the appendices. It's entitled Students' T-Distribution. All right, and it's 2 pages. And so This presentation, I like this presentation in this book for confidence intervals. Very easy presentation on what the T-score should be. And so what you do is you look at the first page and you go over to the left. See at the far left where it says degrees of freedom? Everybody see that? And it goes in the first column, 1 to 35. If you go to the middle of the page, it says degrees of freedom, it goes 36 through 70. Everybody see that? Then you go to the next page and you see 71 through infinity. Everybody see that? Okay? So, degrees of freedom. Well, let's see if that's highlighted in the handout. Okay, so confidence interval estimates for mu are as follows, blah, blah, blah. And it says where. Okay, so here it says T sub alpha over 2, comma, n minus 1 as a subscript at the bottom of that table. I'm sorry, at the bottom of the page. Everybody see that? It says, is the appropriate T-score given the level of confidence and the degrees of freedom? And so what are degrees of freedom in this case? Little n minus 1. So over here, we have what as degrees of freedom? It's equal to little n minus 1, which is equal to what? What's little n? Sample size. Minus 1 is how many degrees of freedom do we have in this confidence interval? 99 degrees of freedom. Okay? And so when you go back to the table, you find 99 degrees of freedom. And is it listed, 99 degrees of freedom?
Yep.
Excellent. It's listed there. And so then the question is, well, what column should we be plucking off the T? And so what's the first column to the right? If you go up to the top, it says 80% confidence. What do we have here for confidence? 95. You go to 95, which is the third column. You go down to 99 degrees of freedom. What do you get? 1.984. Everybody see the 1.984? And so that's the T. So over here, yeah, all right. So we'll just remember that it's 1.984. Okay? Now, if you go down to the bottom of that column, what's the T?
$1.960.
1.96. Zero, right? 1.96? 1.96. Where have you seen that before? That's Z. That's the Z, 1.96. So as I was saying over here, as the sample size increases, the T approaches the Z distribution. Now it gets there because it's an infinite sample size, which never is the case. All that says here is that as n increases, the T moves towards 1.96. And what is it right now? Is it above 1.96 or below 1.96?
Above.
It's above with 99 degrees of freedom. It's not it's not less than 1.96. It's 1.984. And so when you plug in 1.984, what do you think is going to happen to the interval? Is it going to be tighter or wider?
Wider.
Wider. Why? Because you're multiplying by 1.984 versus 1.96. Bigger number, multiplication. You'll see here, that's what's going to happen. That the interval is going to get wider. And we have all the same information, almost. And then we'll ask you, well, why do you think it's wider? But we'll get to that in a minute. So, formula, probability, x bar minus t, alpha over 2, n minus 1, s divided by the square root of n, and then this is a finite population correction factor, correct? Because we know, oh yeah, we said n is equal to 2 million. Didn't we say that in the last one? Mm-hmm. Yeah, so we'll put that up here in this one. And then it's, so it's big N minus little n, big N minus 1, less than or equal to mu, less than or equal to x bar, plus t alpha over 2, n minus, and these are subscripts down here, s divided by the square root of n times big N minus little n, big N minus 1 is equal to 1 minus alpha. No, I kind of forgot, but We went through this and ended up in the T box, right? Yeah, okay, good. All right, so we already know it's a T distribution. Is this a large or a small sample? This is a small sample. Why? Because the population size was given. And so therefore, here's the formula that comes out of the handout, correct? This is the formula that came out of the handout, right? So all we have to do now is just plug in the numbers. And so it says probability X bar. What's X bar? 87. That's what it was before. We'll get to T in a minute. Oh, actually, we know we did T. What did we say it was? 1.984, correct? 1.984. S was 15 minutes divided by the square root of 100 times 2 million minus 100 over 2 million minus 1 less than or equal to mu less than or equal to 87 plus 1.984, 15 over the square root of 100 times 2 million minus 100 over 2 million minus 1 is equal to 0.95. A little better board management, have to go on the other side. And so then we just solve over here. So we got probability 87 minus 1.984 times 1.5 times 0.9999 less than or equal to mu less than or equal to 87 plus 1.984 1.5 0.9999 is equal to 0.95. And so we get probability 87 minus this. What's this over here? What's 1.984 times 1.5 times 0.9999? It's 2 point, maybe it's 3 point something. What is it?
It's 2.97 or 2.98.
2.98 less than or equal to mu less than or equal to 87 plus 2.98 is equal to 0.95. And so once again, we'll just move it over to here. And so we have this as our estimate. Probability, what's 87 minus 2.98? So it's 85, 84.02 minutes less than or equal to mu, less than or equal to 89.98 minutes is equal to 0.95. And so here's our estimate for mu, and this says we are 95% confident that mu is between 84.02 minutes and 89.98 minutes. Is that a tighter or a wider interval than when we knew sigma? Because like I said, the only difference here is that
It's wider.
S is the sample standard deviation, sigma was the population standard deviation, and nothing else changed. We have the same sample mean, we have the same, well, we had the sample standard deviation was equal to the population standard deviation, which forced us into the T to make degrees of freedom. And we have 99% confidence, 95% confidence. And so is this a wider or a tighter interval? And the answer is this is a wider. Why is it wider? Well, the reason why it's wider from a mathematical standpoint is this is 1.984, whereas with the Z it was 1.96. But intuitively, why is this wider? Why is with 99 degrees of freedom 1.984? Well, basically it goes something like this. Remember, in statistics we use all the information to make our estimate. Here we used all the information. What was the difference in information here versus in the last one? In the last one, we knew sigma, right? Sigma is a parameter. This case right here, we don't know sigma. What's sigma? The population standard deviation. This case, we don't know sigma, we know S. What's S? The sample standard deviation. So what's it better, in making an estimate, is it better to know the actual parameter when you make the estimate, or is it better to know a sample statistic when you make an estimate? It's always better if you know the parameter because you don't have to estimate it. So basically what's happening here is you're using an estimate, S, to make an estimate from you. Whereas in the last one, we didn't have to estimate the parameter because we knew sigma to estimate the parameter. So when you use an estimate to make an estimate, what happens is you lose what they call a degree of freedom. And so basically statistics says, wow, if you know the parameter when you make an estimate, we're going to give you credit for that. If you don't know the parameter and you have to estimate the parameter, like S, then we're going to make some deductions for that. Meaning you have to come up with a wider interval because intuitively that makes sense. When you know something, you should come up with a better estimate than when you don't know something and you have to estimate it. So that's the reason why the t-distribution is the way it is versus the z-distribution. Because in the t-distribution, we're using a statistic to estimate the parameter sigma. And we're using this statistic to make an estimate for this parameter, which is mu. Okay, makes sense? What we've done here is we've made use of all the data in constructing our estimate for mu. Let's see, let's go back to the text just for a second. I'm going to flip through here, make sure I'm covering everything in here. Confidence intervals, point estimate for the population mean, confidence intervals for the population mean. It shows you how to read Z when the standard deviation is known. And then there's the confidence interval on page 302 in box 9-1. It says x bar plus or minus Z times alpha divided by the square root of n. The page 306, population standard deviation, sigma is unknown, and it gets into describing how to read the t-table and what a t-distribution is. 307, there's a little decision tree on page 309, but the decision tree I handed out I like a little better. There's also in 9-2, the green box, it shows you confidence interval for population mean sigma is unknown, so it says x bar plus or minus t times s divided by the square root of n. And so then we come to 313, confidence interval for a proportion. Okay, so that's what we'll do. Can't fall down. Imagine if that's on video.
He'll be on America's
That's right.
Funniest
Yeah,
Home
there
Videos
you go.
then.
Exactly.
I'll make sure I get it.
Yeah, there you go. And so, are people following the presidential primaries?
Yes.
And so every minute, every day, they say, oh, and so-and-so is predicted to, is ahead in the polling. And so what's polling? It's this. It's sampling voters or potential voters because they don't have time and they don't have money to survey every voter. The only time that they survey every voter is when? In the election, in the final election. That's only when you get the actual parameter. But they're always trying to estimate the parameter, always trying to estimate who's ahead, who's behind. Why are they voting for this person? Why are they voting for that person? And so what they do is they do statistics. They sample a population of voters that are coming out or going in or whatever it is that they're doing. They take the sample data and they plug it into a confidence interval for pi, because what's pi? Pi is the percentage or the proportion that are going to do something or will do something or have done something. Okay, so let's say that we're trying to estimate percentage to vote for, I don't know, let's say anybody. For, let's say Trump. Today. Well, the election's already over, but tomorrow in some other state. So what they do is they say, okay, we're going to estimate the percentage by way of a confidence interval construction. So the first question is, how much confidence do you want? You want 99? You want 95? Typically, they use 95. Sometimes they even go less, to like 90. Because what happens to the interval when you go from 95% confidence to 90% confidence? Oh, I did not do that, but what you will find out is that if you went from a 95% confidence interval to a 99% confidence interval with the same data, what do you think would happen to the confidence interval? Well, what happens? Z goes from 1.96 to 2.57. So instead of multiplying numbers by 1.96, you multiply it by 2.97. And so that makes a bigger number. And that's added and subtracted to the sample mean. And so you get intervals that are wider when you go for less confidence. But what happens is that it presents better to the public. They say, oh, it's somewhere between here and here. And then in the little subscript at the bottom it goes, well, 90% confidence versus 95. 95 is being wrong 1 out of 20. 90 is 1 out of 10. So basically, if you use 90% confidence and you do 50 states, you're going to be wrong on 5 states. Because 5 divided by 50 is 10, or 45 divided by 50 is 90. So theoretically, if you go to 90% and you do it for all 50 states, those predictions should be wrong in 5 states. And typically, they are. And they're like, wow, what happened in that state? Well, that's just normal. If you want to go to 99% confidence, meaning if you only want to be wrong in like maybe 1 state, then you have to go to 99%, but the interval gets wider, and it's much tougher to call the winner because the intervals are wider, and when intervals overlap, they can't predict the winner because the intervals overlap. And one of the things that I forgot to say is that, when we said that the interval was between, what did we say, it was 84 to 88 minutes or something like that. Is that what we said? 89, 84 to 89. We can't tell what it is. It could be 84, it could be 89, it could be anywhere in the middle. Any one of those could be it. We can't say it's 84, we can't say it's 89, we can't say it's 87. Any one of them is possible.